Hi, Bobcats. In this video, we're going to take a look at standard states and some calculations involving standard states. Um, eh, the way I tend to think about the issue of standard states is that thermodynamics is so picky about all kinds of details, and standard states are just certain conditions that we apply to our reactions. And when we're working at those standard states, we're going to indicate that with a superscript of a degree sign on our symbols, which we read as the word not. So for instance, if we have delta S and it has that degree sign on it, we would read that as delta S not. And whether the not is there or whether it's missing, it has implications for our calculations. So always pay real close attention to whether that standard state is indicated or not when you're doing thermodynamics calculations. So our big objective is to calculate delta G naught, meaning standard conditions, using delta H naught of formation, S naught are standard entropies, and delta G of formation naught at all of that indicating those standard conditions. All right, so standard states are specified by a set of rules. A pure element in its form that is thermodynamically stable at 1 atmosphere and 25 degrees C. That would be a standard state. So for instance, iron as a solid would be the standard state, or oxygen in the form O2 gas would be a standard state. If we have a gas like O2 gas, it's at 1 atmosphere of pressure. A solid or a liquid needs to be pure. And if we have a solution, the solute needs to be 1 molar. And we're going to indicate that we're at standard conditions with that degree sign, and we're going to read it as naught. So for instance, delta H with that degree sign would be read as delta H naught. On this slide, we're going to review how you calculate delta H for a reaction. I can see I already left off a naught here. This should be delta H naught. Back in chapter 6, we had this big long equation. Let me go ahead and advance the slide a little bit to get all of the symbols defined. Okay, so if we're going to calculate delta H naught of the reaction, we are going to take the sum, right? That capital Greek sigma means sum, and what we're going to add up is for all of the products, we're going to multiply their coefficient, which is symbolized by N, times the heat of formation, the standard heat of formation. That's what we go and look up in a table. So we'll take coefficient times standard heat of formation, add that up for all of the products. We'll repeat that process for the reactants. We will add up the coefficients times the heat of formations for all of the reactants. And then we will take that sum of the products minus the sum of the reactants, and that'll give us delta H naught of the reaction. Okay, so just to review, hopefully that process seems somewhat, at least vaguely familiar from Gen Chem 1. All right, let's look at the calculation of delta S naught. We can do it pretty much the same way that we did the delta H in Gen Chem 1. We have a very similar reaction, or sorry, very similar equation. We're going to take the coefficients times the standard entropies for the products and add all of that up. And we'll take the sum of the coefficients times the standard entropies of the reactants, add all of that up, and then take products minus reactants. The one thing that is really kind of different here is that what is found in the tables for entropy is a standard entropy. This is just an estimate or a measurement of how much entropy a compound has at the temperature of the table. It is not associated with a formation reaction, so it's not a delta S, it's just a plain S. So in parallel to that equation for delta H's, we can do the same process to find delta S for a reaction. For calculating delta G naught, we also have that big granddaddy equation like we have for delta H and delta S. But there are actually a couple other pathways. I guess you could do these with delta S as well, but usually problems pop up involving delta G. We could use the equivalent of Hess's law, right? So Hess's law was when we would take various reactions and add them together to give a net reaction. And as we manipulated those equations, we had to do some things to the delta H values. And then once we got them in the right arrangement and we added them all up to get our net reaction, we could simply add the delta H's to get the delta H for the net reaction. So we could do something like that with delta G's. And then we've got another process available to us with Gibbs free energy, and that's the equation that delta G is equal to delta H minus T delta S. And if we want to make this all at standard states, we would have delta G naught is equal to delta H naught minus T delta S naught. And not to get too caught up in the notation, but sometimes we won't know the delta H or the delta S under a particular set of conditions, say like a different temperature. So we actually can approximate delta G under non-standard conditions with delta H naught minus T delta S naught, recognizing that we'll probably be off a little bit because we're using standard delta H and delta S values under non-standard conditions to estimate delta G. All right, let's work our way through this problem. We need to find delta H naught, delta S naught, and delta G naught. The reaction that we're given is two SO2s react with O2 to make two SO3s. And it's carried out at 25 degrees C in 1 atmosphere. So under standard conditions, let's calculate delta H naught, delta S naught, and delta G naught from the following data. So this is one of those scenarios where we have to look at the data we're given to decide what path it is we will take for calculating the data that we're asked to find. And so here we are given the standard entropies for these three substances. We're also given the standard enthalpies, delta H is a formation. So we can use this data to calculate delta H of the reaction and delta S of the reaction. And then once we know those values, we can calculate delta G from delta G equals delta H minus T delta S. Whew. That's going to be a lot of steps. So there's not enough room on this slide to work all of this out. I took a photograph on my phone of this slide. I'll be using that to pull up data. You may want to pause this video and grab a photograph or a screenshot yourself, and then we'll move on to the next slide and do the actual calculations. All right, for reference, the chemical reaction that we're working with is two SO2s react with O2 to make two SO3s. All chemicals are in the gas phase. I should probably write that in. All right, and so we were given the heat of formation data, and we can use that to calculate delta H. So I'm not going to rewrite that whole big equation again, but what we're going to do is take the coefficients times the heats of formation for the products. There's only one product. It has a coefficient of 2, and the delta H of formation for SO3 is negative 396 from the previous slide. And then we'll subtract the summation of the coefficients times the heats of formation of the reactants. So for SO2, we have a coefficient of 2, and the heat of formation of SO2 is negative 297. And then for oxygen, there's only one of them, and the heat of formation of any element in its standard state is 0. So O2 is 0. Very often those values will not be given to you since it's just 0 for the element in its standard conditions. Okay, so in that first set of brackets, I've got 2 times a negative 396. And so that first set of brackets gives me negative 792. And then we're going to subtract what we have in that second set of brackets, which is 2 times a negative 297. And so that second set of brackets gives me a negative 594. Minus a minus gives us a plus. Math teacher I knew used to call that tick-tock when you make the little slashes to convert two minuses to a positive. And so delta H for this reaction will be the negative 792 plus 594, which will give us a value of negative 198, and the units on that are kilojoules. So there's our delta H. To calculate our delta S, we'll go through the same process. We'll take 2 times the standard entropies of the products. Let's see, that's SO3, so that's 257. There's only one product. Then there were 2 reactants. We have 2 SO2s, and the standard entropy of SO2 is 248. Now the standard entropies of the elements will not be 0, so we do need to add in the standard entropy for O2, which is a 205. And then years of experience of doing these types of equations have taught me to just go ahead and calculate the square brackets individually. So for that first one, 2 times 257, I get a total of 514. And then we'll subtract the second set of square brackets. And that was 2 times 248 plus 1 times 205, which gives us a 701. So now I'll just subtract those two values, and I will get that delta S is equal to a negative 187. Now remember that entropy is in slightly different units. This will be joules per Kelvin, and I can see I've already forgotten my knots. Those should all be knots. And then let's see, in order to calculate delta G naught for this reaction will be delta H naught minus T delta S naught. And let's see, for delta H naught, we had a value calculated right on this page of negative 198 kilojoules. And our temperature was given as 25 degrees C, which converted to Kelvin, that's 298 Kelvin. And then our delta S value was a negative 187 joules per Kelvin. I'm going to go ahead and convert that to kilojoules to make it compatible with our delta H and the normal units for delta G. So I need to move that decimal 3 times, and this will be negative 0.187 kilojoules per Kelvin. Go ahead and write that in. It's a negative 0.187 kilojoules per Kelvin. The kelvins cancel out. The only units we have left are kilojoules. All right, so we've got the negative 0.187 times a negative 298. And so let's see, that's going to be negative 198 plus 55.726. And so running those two numbers through my calculator, I end up with a delta G of negative 142 kilojoules. All right, so we were asked to find delta H, delta S, and delta G, and that is what we end up with.